Okay, let's go ahead and get started. This is week number 10, so we should be seeing the light at the end of the tunnel. Not everyone necessarily has made the progress they would like, but we still got several more weeks to get things all pulled together. The good news is this is the last week in which any new technical material is being introduced. There are no more peripherals to learn about after this week. The rest of the semester will be just getting all the previously learned peripherals to work in the way that you want them to work. So that's the good news. This is the last week to learn about a new peripheral. The bad news is it's probably the most complicated peripheral that we have, in the sense that it has a lot of options. It is a very capable peripheral device. And so my advice to you is don't try to be overly ambitious this first week. Maybe try to run it in its most basic mode. And then if you have time permitting the rest of the semester, you can try to explore some other modes. Okay, so it's complicated only from the standpoint that there are a lot of options, but you don't have to use all those options to have a very successful semester. Okay. This is a week for turning in lab notebooks, so do the best you can this week in lab. I believe this is the last time the lab notebooks will be graded, per se. Okay. I am working on grading the draft reports that you wrote about experimentation. I should have them returned to you on Monday. That leaves you, I think, about 10 days to revise and then resubmit. So the university would like every student to have a experience where they revise something that they wrote, and so this is where we do it right now in our curriculum, is in this particular report. Are there any questions about what's coming up? All right. You have one more written assignment. You're going to revise that, and then at the end of the semester, you'll have an oral presentation during the last week of class. That's after Thanksgiving break. Okay, so, and then everything else is all lab work. All right, so we're going to turn our attention this week to this device, the analog to digital converter peripheral inside the microcontroller. Okay. We're going to take a look at the tachometer signal again. Last week, what you tended to do was to try to time the period of that signal by using a timer in input capture mode. Okay. This week, we're going to take a look at the amplitude of that signal. And so we're going to try to measure that amplitude with the A to D converter, analog to digital converter. And it's all part of the motor speed control project. Now, after this week, you and your teammates will have to make a decision. Do I want to measure the amplitude of the tach signal, or do I want to measure the duty cycle? And so you get your choice for the final project about which way you want to approach this. As I said, this particular peripheral has a lot of options, a lot of features. You don't have to use all of them. I recommend you not try to do it all at one time. I encourage you, I won't be able to cover everything in all its details simply because the peripheral is just that complex, but I'm going to try to hit the high points about the features you need to be aware of, and then you can decide which ones you want to avoid initially. But in the reference manual, L100, we are in chapter 12. So chapter 12 is kind of a long chapter talking about the A to D converter. So if you want to get some more details, consult the reference manual. All right, so this is the block diagram, again, of the overall project. I'm sorry it's a little bit dark here. I'm going to have to lighten that up a little bit. This is just showing all the basic hardware elements. We have a motor tachometer unit. The motor is driven by an amplifier, which you built several weeks ago. The amplifier is supplied by 9 volts from the EE board. The amplifier has an input. It's a PWM signal from the microcontroller. And the microcontroller this week is going to take a look at the tachometer signal's amplitude. And this is an AC signal And what we're going to do is we're going to convert it in time to something which is approximately DC. And we're going to try to measure that amplitude using the analog to digital converter. So I apologize that this is a little bit dark here. The printer, it's a lot lighter on my computer screen, but on the printer it came out a little bit dark. This says AC to DC. We've got to convert this AC signal to DC. And then this is the analog to digital converter. And so we're going to go through these stages here. And then the analog to digital converter is going to give us a reading in bits, which is supposed to be proportional to how big the amplitude of that signal is. All right, so that's the idea that we're going to look at this week. The A to D, the AC to DC converter or circuit is very simple. There are no, no active elements, and so not like where you had to deal with a comparator. So this is a very simple circuit. But this animal here, the analog to digital converter, is a little bit complicated, sophisticated. So this is a block diagram of the typical A to D converter subsystem that is used in many microcontrollers. We have one element that basically can do conversions of an analog signal and turn it into a certain number of bits. So this is the A to D converter. But many times in life, the microcontroller may be looking at multiple properties, maybe pressure, temperature, so on and so forth. And so each of these different properties may need to have some sort of signal conditioning. Right here, signal conditioning. The property is sensed by some sort of thing that we call a transducer. A transducer is something that it's trans. It means it changes. It changes the property from its normal state. And so for us as electrical engineers, a transducer typically will change some property like temperature or weight or speed to some sort of electrical variable like voltage or current. So that's why it's called a transducer. It means it's going from one state to an electrical state. And then once we turn it to an electrical state, maybe this voltage or this current is not at a level that is appropriate for processing by the A to D converter stages later on. We may have to amplify it. We may need to filter it. So that's signal conditioning. So that's what we have to do this week. We have a transducer. It's basically producing an AC signal. The tachometer is taking, say, speed. Let's call that one of the properties. It's taking speed, producing an AC voltage. Now, our signal conditioning is going to take the AC voltage and turn it to a DC voltage that's in the correct range. Then we can process it by the rest of the A to D converter. There is a thing called a multiplexer. The MUX basically allows us to choose which channel we want to deal with. Up to 16 regular channels. There are actually more channels than that in the device. Among the external channels, we can look at 16 of them. There are a bunch of other internal variables that could also be looked at, but this we can look at up to 16 channels. All right. Sometimes signals vary more quickly than it takes us the time to do the conversion. Conversion takes time. Converting from analog to digital takes a little bit of time. And we'll understand a little bit better this afternoon after I discuss some of the ways that we do conversion. It takes a little bit of time to work. And what we want is that while we're working, that the signal that we're working doesn't change its value. Because we're trying to measure its characteristic. But many times that signal may be continually changing. And so what we do is we say, well, if it's going to change, I need to freeze it for a moment, and that's called sampling it. So we sample the signal, and we hold it, and we work on the held amount while the signal continues on evolving over time. So all these elements you see here are inside the microcontroller, the MUX, the sample and hold, and the A to D converter. This week we'll build a very simple signal conditioning circuit to basically convert AC to DC. Okay, so this is a very typical way of handling conversion of multiple properties to their respective digital values. So what are the goals of signal conditioning? The main goals of signal conditioning is to try to produce a signal that's as noise-free as possible, minimize the noise, and have it be within the range of the A to D converter. Now, for our A to D converter, we have to have signals in the range of 0 to 3 volts. Okay? So in our particular case, we need, in this lab, to convert the AC signal, the AC tachometer signal, to a DC signal. Okay? We can do that with a rectifier. The signal can also be too large. It's not going to fit in this range after it's been rectified, so we may need to attenuate it. In some cases, some applications, you may need to amplify things. So for example, if you're looking at a thermocouple voltages, thermocouples convert temperature to a voltage, and those are typically in the order of millivolts. So you may need to amplify it for your A to D converter. Sometimes you might need to shift the signal, add a bias to it. May need to filter it. We're going to have this element. We're going to have to filter it a little bit. We have to do this. And sometimes you get a signal which is being sent to you on multiple channels, on 2 channels. So for example, USB, there's a data plus and a data minus. And a lot of communication channels, they have plus and minus. And basically what they're hoping is that if there's noise, noise will affect both channels equally. And then what we'll do is we'll take the difference between the two. And when we take the difference between the two, then what is so-called the common mode noise, the noise that is common to both channels, gets rejected, gets subtracted out. It gets eliminated. And then what's left is what's different between the 2 channels. And then sometimes we deal with signals that are frankly, they're just at dangerous levels. So in industrial motors, for example, we may be dealing with AC voltages that are at hundreds of volts. And so we need to maybe measure currents that are hundreds of amperes, and we cannot deal with that with our little microcontroller. And so we want to isolate ourselves for safety purposes. And so a lot of times we may use things like transformers or optical isolation to isolate ourselves from those dangerous signals. We don't need to do all these things this week. We primarily just need to convert AC to DC and do a little bit of filtering. So this is an example of AC to DC conversion. The AC signal is shown up here. We'll call that an unrectified signal. We have a couple options. One option is to do what we call a full wave rectification. That means all of this negative stuff becomes positive, like so. Okay? So this is called a full wave. And then what we want to do is we want to then try to remove some of this ripple. And so what we will do is we'll filter it to try to minimize this ripple. So this is what we call a rectified and then filtered signal. Now, one way to do that, before we get that, we could also do a half-wave rectification. Half-wave rectification means you simply ignore the negative parts, and we're just left with a half wave. And then what we can try to do is try to filter it. This is a simpler operation. It's simpler than trying to do a full wave rectification, but you get longer gaps where you have no information. And so if you're using, say, a filter, then you may be gradually losing information over time. And so you have larger ripple with a half-wave rectifier. So this is an example of a full-wave rectifier. This is the tachometer. This is a SPICE simulation. 4 diodes arranged this way. So the AC signals are applied here. And then what you read here is the rectified signal. And so this signal here, the AC signal, is this signal here. And then at the output, what we have is, you got to imagine yourself, if you didn't have this capacitor, it would just be full wave rectified. So imagine having this signal and then having this signal and so forth. Okay? But what we have here is we have a full wave rectified signal that is then filtered. And so we see that there's this ripply kind of signal here. And that ripple depends on this RC time constant here. Okay? So what we want to do is we want to try to minimize the ripple, but there's a trade-off there. Because if the RC time constant is made really large so that we can reduce the ripple, then as this signal grows and shrinks, gets bigger and smaller, it may take a long time for that filter to respond, to move the output up and down. So there's a trade-off there. Okay? This is an example of a half-wave rectified signal. So here's the AC tachometer signal. It only takes a single diode, and then we have our low-pass filter. And so you can see that the ripple here is a little bit larger than for the case of a full-wave rectified signal. All right? So let's talk a little bit now about what is the process of analog to digital conversion. What does that mean? It means that we're going to take a continuous time signal, v of t, and convert it to samples. And here, this is sample data, and we're going to sample it every t units of time. And so n here is an integer, 0, 1, 2, 3, 4, and so forth. Okay? So Vn of t is v of t measured at the nth sample time. Sometimes in some of my courses, what I'll do is I'll emphasize that this is a digital signal and this is an analog signal by maybe writing this as V n t and using square brackets just to kind of remind ourselves that this is in sample domain, discrete domain, and this is continuous domain. Okay? So what is going to happen is we're going to convert this at every sample and to a number of discrete, a number of discrete levels. And so if we have a k-bit number, that means we can have up to 2 to the k values. All right? The sampling time is the time, if we have a signal like so, we're going to periodically sample it. This is the sampling time t, and we're just going to pick off the values here. I sketched that in the next picture. This is the process. This is the analog signal, and this is the sampled signal. Okay? This is the sample signal. It means that every t units of time, we pick off the actual value right here. Okay, so this is the sampled signal. The signal doesn't exist for all time. It only exists at the sample instance, t, 2t, 3t, and so forth. Now the reality is, not only is it sampled, but our A to D converter has a certain amount of resolution. I said earlier we have to produce and say, what is this value? What is the closest value? It's got to be one of the 2 to the k numbers. And so here's an example where we're going to quantize it and say that maybe we have a 2-bit quantizer. A 2-bit quantizer gives me up to 4 levels. Okay, 1, 2, 3, and here's 0. Okay, so this is one level, 0. Next level, second level, the fourth level. First, 1, 2, 3, 4. And so even though the sample data would be these dots, after I quantize it, what I have to do is the A to D converter will say, well, let's take this level. Which one of these 4 levels is most close to this one? It'll be this one. How about this one? What is most close to this level? It'll be this one. When I get to this particular level, I may say, what level of these 4 is closest to this level? It becomes like this. And so my data actually has been sampled in time and then quantized vertically. You see, it's far away really from what the analog signal looked like. This is the information that I get in the sample data sense. I think the actual analog signal is doing this, but I think, after I sample it, I think this is my data. So this is the issue that we have when we use digital control of the real world. There's information loss because I don't have all the information here between samples. And there's also information loss, accuracy loss, because I've assigned the nearest value to the analog value. Okay. Now, it turns out that there is a thing called the sampling rate, the Nyquist sampling rate. It says that in theory, if we sample at least twice the bandwidth of the signal, then we can recover the original signal. We need to sample at least twice the bandwidth. So for example, music, we usually think of it as having a bandwidth of 20 kilohertz. But a CD quality music is typically sampled at 44.1 kilohertz. Okay, our hearing range is, well, for me, I'm lucky to be hearing above 12K at my age. My dog does better. You guys, I hope, are doing better. So this is the theory. The theory is that if you sample at least double the bandwidth of the signal, you can recover it. It means that you have all the information forever. You have an infinite amount of information, but it's sampled at least double the speed. The reality is you don't have an infinite amount of information. You don't have an infinite number of samples to work with. And so what we typically do is we will sample a little bit faster than 2 times the sample rate. Rules of thumb, a lot of times we may sample at 5 times the bandwidth or 10 times the bandwidth. With the CD player, we don't have to go 5 or 10 times because all the data for that song is on the disc. And the disc just goes round and round, round over again. And the computer can say, hey, I missed a bit. I can go back and read it again. And so as the platter is spinning, we're getting more and more information. We can recover all the information. We have the entire song there. And so we don't have to go 5 times or 10 times this. There's a lot of sophisticated signal processing that allows us to recover the music even at a very high fidelity. We just have to go a little bit beyond 2x. Okay? In the old days, telephone system was an analog system. Now, a lot of digital telephone is sampled at 8 kilohertz because we are just trying to capture voice. Okay? None of us are listening to opera over our cell phones. Okay? And we're just trying to get information across. And most of our information in our voices can be captured in a bandwidth of about 3 kilohertz. And so they sample it at 8 kilohertz. Okay, so that's talking about how often we sample this way, horizontally. Okay? We need to sample this way in time often enough so that we can recover the information. Okay? But we also are concerned about the error vertically, and that's quantization. And that's the number of bits that are used to sample data values. And so k is the number of bits, and I already said that if you have used k bits, then you have up to 2 to the k values, including 0. Okay? So accuracy is the degree to which the converter gets the correct value. Okay? I talked a little bit earlier about the sample and hold. So this is the sample and hold. It's basically a capacitor and a switch. And so this signal here may be varying slowly. And you're trying to convert it to a digital value, and it's a moving target. And basically, you want to say, hey, hold still while I work on you. So the way they do that is they close the switch for a moment, and they allow the signal to charge the capacitor for an amount of time. So here's that signal. We close the switch for an amount of time. This time is sometimes called the aperture time or the sampling time. We close it for an amount of time to charge up the capacitor, and then we open it. We open it, and then now we have a voltage here. This signal can continue to vary, but this signal here now is held, it's constant. This sample time is programmable, so that's one of those options I talked about. Okay? Let me back up. Let's talk a little bit about options. I said one of the options is you got multiple channels. Okay, so bear that in mind. We have to select which channel we're going to work on. The other thing we got to deal with is the sample and hold. How long are we going to sample or charge up this thing? Okay, that's something that has to be considered. If it's a signal that's changing quickly, then we probably want to sample for a short amount of time. But if it's a very, very slow signal, then we could extend the amount of sampling time or aperture time. What that does is it helps remove the noise because we're averaging. You know, a capacitor is a filter, low-pass filter, so it averages. So there's a trade-off with the sample and hold and the amount of noise that is in the signal, how much of it is removed there. Okay, we're talking about A to D conversion, but in order to understand A to D conversion with many A to D converters in the microcontroller world, we have to understand D to A, digital to analog. And so at the heart of a digital to analog converter is what is commonly known as an R2R ladder. And so this is the R2R ladder, and if you kind of zoom into it, you see the other resistors have only one of two values. They're either R or they're 2R. R and 2R. R and 2R, like so. Okay? So basically what happens is, what they do with a D converter is there's a reference current. There's a reference voltage. All this ladder is set up, and there's a reference current that flows through here. And so at each node, a little bit of current gets peeled off. A little bit more current gets peeled off. And if you do a little bit of analysis, say working from down here at the least significant bit and working your way back up, what you discover is that the equivalent impedance looking down here is just R. Let's take a look at that. Let's take these two legs. Looking down here, if I'm sitting here looking down here, I see two resistors, 2R and 2R in parallel. So the parallel combination of 2R and 2R is R. And now I take that and put it in series with this resistor, and it's now 2R. So this looks like 2R in parallel with 2R. So sitting here, it looks like R. We keep on going. So no matter where we are, looking down, it looks like I have a resistance of R. And so the amount of current that's flowing through here is just VR, the reference voltage divided by R. But the amount of current that's flowing through these different legs, when they're switched, each of these is related to half of the current above. So here I have 1/4 the current that I have here. Here I have half the current that's here. Because these legs are splitting, they're parallel. They're two resistors, two equal resistors in parallel. Half the current goes here, half the current goes there. So here I have a certain amount of current, half goes here, half goes here. Then a fourth goes here, and a fourth goes here. Then an eighth goes here, and an eighth goes here. And keep on going like this. Then what we do is we control a bunch of switches. We allow these switches to either shunt the current to ground, so the current can flow here and be shunted to ground and basically be thrown away, or the switch allows it to come into this summing junction right here. And so these currents, these switches, depending on whether they're 1 or 0, allow these currents to either be shunted to ground when it's 0, or they get summed into this summing node right here. And then so all these bits, this is the least significant bit down here and the most significant bit up here. These bits basically are a way of adding up all the currents from all these ladder legs. Each ladder leg has, this ladder leg has double this current, this is double that, and so forth. And that's a weighted sum added together, and that produces a current out here, which is related to the bits in my n-bit number, 0 to bit n. And so this then produces a voltage. This is just a inverting amplifier, and it produces a current to voltage conversion. Okay? And the idea is basically this R to R ladder network. This is used because we only need to have 2 resistor values, and so in a micro fabrication process, it's easy to laser trim these resistor values so they're very, very accurate and they match each other. And I only need to have other resistors that are also 2R. So basically, I just need to make R-size resistors. Here, I can just put them in series and get that. And I can make a very, very accurate ladder. There are other types of ladders that use weighted resistors, but that means you got a ton of different resistor values that have to be built, and getting it accurate is a problem. So this, the D to A converter, is actually at the heart of the most common type of A to D converter, and that is called a successive approximation A to D. The way the successive approximation A to D works is like this. We have a register, it's clocked, and it basically is controlling a bunch of bits. Its output here is a bunch of data bits. And so this is data bit 0, data bit 1, 2, 3, up to data bit n minus 1. So this is a total of n bits. We take those n bits and run it through a D to A converter, this R to R ladder.